Assalamualaikum and hello everyone. My name is Muhammad Nazirul bin Zuki and my metric number is 285469 and I would like to present about the linear programming. In this video, I will graphically solve a basic linear programming problem using the extreme or corner point approach. What I have here is a linear programming or LP model. The x and y in this model are referred to a decision variable. They tell us what quantity to buy, produce, sell, or transport, and so on. The 2x plus 5y here is referred to as the objective function, which I want to maximize. In linear programming, I either maximize or minimize the objective. The next two lines are called constraints. They are restrictions that shape how you attain the objective. Let's call them C1 and C2 for reference purpose. Since I'm dealing with a real-life object, I did not expect them to have a negative value. So, the last line here tells that both x and y to be greater or equal to 0. We call them the non-negativity constraint. To solve this model graphically, I begin by finding points that satisfy the constraint line. For the first constraint, when x equal to 0, y equal to 8, and when y equal to 0, x equal to 16. For the second constraint, when x equal to 0, y equal to 15, and when y equal to 0, x equal to 9. Now, when drawing the graph, I usually just stay in the first quadrant here, where both x and y are positive because of the non-negativity constraint. So for the first constraint, I have the points 0, 8, and 16, 0. I join those 2 points for the constraint line. I do the same for the constraint 2, 15, 0, and 9, 0, and then draw the constraint line. Since these constraints are less than or equal to constraint, they will be certified in the regions below the lines towards the origins. Therefore, the region certifying both constraints simultaneously is the one here. That is called the feasible regions. That is, any point in this region is a feasible solution. In particular, the optimal or the best solution will occur at an extreme point or a corner point of the feasible region. These are the corner points for the feasible regions. Let's label them 1 to 4. The optimal solution to this linear programming problem will occur in at least one of them. To decide which one is optimal, I will find the coordinate of the points, plug them into the objective functions, and then choose the best. At corner point 1, the coordinates are clearly 0, 0, at point 2, 0, 8, and point 4, 9, 0. Now, those are easy to see. For corner point 3, I can see that the coordinates are 6, 5 by eye spelling, that is looking at very closely. But eyeballing is not usually the best way to go when finding the intersections of two lines, especially when manually drawing the graph. So let's see a way to solve the two equations simultaneously to determine the actual coordinate. Here are the lines for the two constraints. Now, suppose I choose to eliminate x. Note that the coefficient of x here is C2 is 5. Then I can simply multiply the first equation by 5 to give 5x plus 10y equal to 80. and then subtract C2 from the new equation. So 5x cancel 5x, 10y minus 3y is 7y, and 80 minus 45 give 35. And when dividing both sides by 7, we have y equal to 5. Now find x. I substitute y equal to 5 into any of these three equations. Suppose I choose C1, then I have x equal to multiply 5 equals 16. That is x plus 10 equal to 16. X equals 16 minus 10, and x equals 6. So the x, y coordinate for extreme point 3 are indeed 6, 5. Next, I determine the optimal solution point by finding the corner point that gives the best value of the objective function. The objective function was to maximize 2x plus 5y. As you can see here, the objective functions or its value is sometimes represented with sets. So now, the x minus y coordinates at point 1 are 0, 0. And substituting that in the objective function give 2 multiplied 0 plus 5 multiplied 0, which equal to 0. At point 2, we have a 0x. So the objective function value is 2 multiply 0 plus 5 multiply 8, which equal to 40. The coordinate at point 3 are 6, 5. So z equal to multiply 6 plus 5 multiplies 5, which equal 37. And finally at point 4 with 9, 0, z equal to multiply 9 plus 5 multiply 0, which gives 80. So here I have it, point 2 provide the highest value of the objective function. So the optimal solution occur at point 2, and it is 8 equal to 0 and y equal to 8. And the corresponding objective function value is 40. And they conclude the solution to this LP problem. Thank you for watching and see you again.